If you've ever stood by the ocean, just mesmerized by the power of the waves, or thought about those huge, invisible currents shaping our world, then you're in the right place. Today, we're diving deep into the science behind it all. This is Ocean Motion.
And it is so true, isn't it? The ocean is never still. It's in constant, powerful motion. But these movements aren't just random splashes. They're part of a massive, global system. A system that pretty much dictates our climate, our weather, and even life itself.
So that leads to the big questions, right? What's the engine behind all this? Why isn't the ocean just a giant, placid lake? We're going to unpack the forces, like the sun and the Earth's own spin, that get everything moving. And we'll see exactly how those forces create the giant ocean currents and the waves that can travel clear across the planet. Here's our game plan. We're going to start with the sun, the ultimate power source. Then we'll see how our planet's spin adds a really crucial twist to the whole story. After that, we'll explore those huge rivers in the ocean. We'll break down what a wave actually is, figure out how they're born, and finally, we'll follow a wave to its crashing end on the shore. All right, let's dive in.
You know, it's kind of wild to think about, but this whole story starts 93 million miles away. It all begins with the sun. It's the engine for almost all the motion we see on Earth's surface, and the ocean is absolutely no exception.
So think about it like this. The Earth is a sphere, right? The sun's rays basically act like a giant spotlight, hitting the equator head-on, just concentrating a ton of heat there. But up at the poles, those same rays come in at a really shallow angle, so the energy gets spread way out. This creates a huge energy imbalance, a big surplus of heat at the equator and a major deficit at the poles. And that imbalance is what gets our atmosphere moving. All that warm, light air at the equator rises up, creating a zone of low pressure. Meanwhile, at the poles, the cold, dense air sinks, creating high pressure. Well, air always wants to move from high pressure to low pressure to even things out. And that movement, that's wind. And this is the very first key to ocean motion. Okay, so if the Earth didn't rotate, this would be super simple. Wind would just blow in a straight line from the cold poles to the warm equator. But, of course, our planet is constantly spinning. And that spin adds a fascinating and seriously important complication to the story, the Coriolis effect.
So here's the thing about the Coriolis effect. It's not a real force, like gravity, that's actually pushing on things. It's an apparent force that just happens because we're on a spinning surface. The best way to picture it? Imagine trying to draw a straight line from the center of a spinning vinyl record to the edge. From your perspective, the line would look curved, right? That's exactly what happens to things moving over long distances on Earth.
Yeah, let's just imagine that non-spinning Earth for a second. It would be so tidy. You'd have this one big, simple circulation pattern in each hemisphere. Cold air sinks at the poles, flows straight to the equator, heats up, rises, and repeats. Just one giant, predictable loop.
But now, let's hit the play button and start the Earth spinning again. Look at that. That simple, neat loop is completely shattered. The Coriolis effect grabs that moving air and deflects it, breaking that single massive cell into 3 smaller, distinct cells in each hemisphere. This is what gives us the complex, curved wind patterns that actually exist on our planet and drive the oceans.
So here are these simple rules of the road you have to remember. In the northern hemisphere, anything moving long distance gets deflected to the right. In the southern hemisphere, it's deflected to the left. This one principle explains the direction of everything from massive ocean currents to the spin of a hurricane.
All right, so we've got our 2 main players on the field. The sun creates the wind, and the Earth's spin gives that wind a curve. With those 2 forces down, we can finally talk about the first major type of ocean motion, currents. And these really are like vast moving rivers flowing within the ocean itself.
Now, it's important to note that ocean circulation is really a 2-story system. Up on the surface, in the sunlit zone, you have circulation that's totally driven by the wind. It's fast, it's dynamic, but way down in the deep, dark ocean, there's a whole other circulation system that's much slower, driven by tiny differences in the water's density. Now here's where it gets a little weird. You'd think that if the wind blows south, the water also moves south, right? Nope. Because of the Coriolis effect, the net movement of that surface layer of water, what we call Ekman transport, is actually 90 degrees to the right of the wind in the northern hemisphere. It's a bit of a mind-bender, but it's absolutely essential for how the big ocean gyres form.
So what about that deep ocean circulation? That's driven by something called thermohaline circulation. The name sounds complex, but it's simple. Thermo for temperature and haline for salt. up in the polar regions, when sea ice forms, it leaves the salt behind. This makes the water left over super cold and super salty. In other words, really dense. That dense water sinks all the way to the seafloor and kicks off this slow, plodding journey around the globe known as the global conveyor belt, a journey that can take 1,000 years to complete.
Okay, so we've covered those huge, slow-moving currents. Now let's switch gears and talk about the other iconic, and maybe more familiar, form of ocean motion, the wave.
This is the absolute most important thing to get about a wave. A wave isn't water moving across the ocean. It's energy moving through the water. Think of it like a pulse of energy that's just traveling through the ocean as a medium. And every single wave, from a tiny ripple to a giant tsunami, has the same basic parts. The very top is the crest. The bottom of the valley is the trough. The height from the trough to the crest, that's your wave height. And the distance from one crest to the next one is the wavelength. Simple as that.
Okay, so this brings us to a super common misconception. When you're at the beach and you see a wave coming in from way out on the horizon, is that the same water traveling all that distance to eventually wash over your feet?
The answer is a big, definite no. What's actually happening is that the individual water particles are just moving in little circles. They go up, forward, down, and back, returning to almost the exact same spot they started in. You know, think of a rubber ducky floating on the ocean. As a wave passes, the duck just bobs up and down. It doesn't get carried to shore. The energy is what's moving forward, not the duck and not the water.
So if a wave is just energy moving through water, you have to ask, where does that energy come from? Well, for most of the waves you see, the answer is an old friend, the wind.
And what makes the difference between a little ripple and a monster wave really comes down to three things. First, wind velocity. How fast is it blowing? Faster wind means more energy. Second, wind duration. How long does it blow for? And third, the fetch. That's the distance of open water the wind can blow across without being blocked. To get those truly epic, giant waves, you need all three. A really strong wind, blowing for a long time, over a huge stretch of ocean.
But you know, no wave's journey lasts forever. They all have to come to an end somewhere. So now let's follow a wave on its final dramatic approach as it leaves the deep ocean and heads for the coast.
As a wave gets into shallower water, it starts to feel the bottom. Friction with the seabed starts to slow the base of the wave down, but the top of the wave, the crest, is still cruising along at its original speed. So the wave gets taller and steeper until eventually it basically trips over itself. It becomes unstable and collapses forward in that beautiful, chaotic crash we all know as a breaking wave.
And fun fact, not all waves break the same way. It really depends on how steep the beach is. On a gently sloping beach, you get spilling breakers, where the white water just sort of tumbles down the front. A steeper beach creates a plunging breaker. That's the classic hollow curling wave that surfers love. And on a really steep shoreline, you might get a surging breaker that doesn't really break at all. It just kind of rushes up the beach.
So when you put it all together, from the sun's heat creating wind to the Earth's spin giving it a curve, which drives the currents, which transfers energy into waves that crash on our shores, you see that ocean motion really is like the heartbeat of our planet. It's this massive, constant circulatory system moving heat around the globe, driving our weather, and shaping the world as we know it. It really makes you think, doesn't it? As our climate changes, which part of this global heartbeat do you think is most critical for us to understand?